Perfect.
Great. We're off.
Yes.
Thank you, Zen.
All right. Wonderful. Yes. So, as Graham so kindly introduced me, I'm Zenny Wettersten. I am a PhD student here at CERN, working in the Future Technologies Initiative to port HEP software to accelerated architectures. And I'm proud to stand here to present our team's work into porting leading order event generation in MadGraph 5a and CERN to data parallel architectures, specifically GPUs and vector CPUs. Before I get properly started, I would like to make 3 comments. The first one is an apology. I would like to apologize. I've been sick for the last week. That's not what I'm apologizing for, but that has left my throat, let's just say, not in tip-top shape. So I may end up coughing during the talk. I may end up needing to take a quick break to catch my breath. So that I apologize for in advance. Second point is that this is, of course, quite a technical talk. I'm not going to go too much into the very nitty-gritty technical details, but I will be assuming at least an elementary understanding of perturbative quantum field theory as well as Monte Carlo methods. And then thirdly and finally, I will completely forego any motivation or justification for this work. Furthermore, I will actually gloss over a lot of the results quite quickly. And the reason for this is because the talk immediately following this by Jin Choi on behalf of the CMS collaboration will go into details on actually implementing CUDACPP into the CMS event generation workflow. So he will have a far better understanding of what this actually means for a real world use case. I'm a theorist. I don't really care about that. But with all of that out of the way, let's actually get into things. So first off, do I have a, can I actually? Nope, doesn't seem to work. Alas.
It looks good.
Yeah. All right, there. Starting off, MadGraph. And before we even get into MadGraph, let's just talk about what we're actually doing in MadGraph. We're evaluating, Never mind. Did I just, okay.
The focus is not.
Yeah, now, yeah, all right. I'm not going to touch the mouse besides clicking buttons from now on. Perfect. Before we actually get into MadGraph, let's talk about what we're actually doing when we're generating events in MadGraph. So MadGraph is a parton level event generator using helicity amplitudes. That's based on Feynman diagrams. It's a Feynman diagram method. And I just want to briefly mention, although I'm assuming in level of knowledge in this, that what you're actually doing when you're evaluating Feynman diagrams is you're looking at your initial state particles, you're looking at your final state particles, and you're looking at every way to map that initial state to that final state. That is to say, it's a topological method. I'll get back to that in a minute. But here we have the formulae you get using Feynman diagrams, but I haven't actually showed you how to evaluate them. That comes here. Now, when we're actually evaluating amplitudes or probabilities or matrix elements or whatever you want to call them, there is one point to take in mind, and that is that we need to sum over every quantum number that is not observed in your detector. Typically, we do not measure spin, at least not directly, which means that we're usually evaluating spin-summed amplitudes. And for pen and paper calculations, this actually allows us to do a bunch of algebraic tricks to simplify the formulae using particularly trace techniques, which is incredibly nice when you're actually doing a pen and paper calculation, but a lot of the time we are not. Which is why numerically, where you cannot really, well, you could, but you don't really want to evaluate these simplifications for every possible process, we just evaluate these spin amplitudes or helicity amplitudes directly and then sum them. What are the pros and cons of such a method? As I already mentioned, Feynman diagram methods scale incredibly poorly. Since they're topological, the complexity grows factorially with the number of external particles. Additionally, we are explicitly foregoing a lot of simplifications by using helicity amplitudes instead of the simplified spin-summed amplitudes. But what we get for foregoing this is generality. Feynman diagrams are incredibly general. Essentially, if you have a QFT Lagrangian, you can immediately pull out the Feynman rules from that to construct Feynman diagrams. And by also doing explicit helicity summation, you know exactly how the helicity will enter into your different particles. So we have full generality in what we can evaluate with Feynman diagrams. This is not just on leading order, at leading order. This scales to arbitrary orders. When you go from leading order to next leading order, you just add one vertex to all your Feynman diagrams. If you go to next leading order, you add another vertex, etc., etc. So this is, I would say, justification for why at least someone should be using Feynman diagram methods, if not everyone, because there are, let's just say, simpler ways to do things in a lot of cases. Nevertheless, that actually brings us into MadGraph. And particularly, I want to talk about the event generator section of MadGraph called MadEvent. It's a parton-level event generator, which means that given this input and output particles that you have in your process, it gives you a bunch of events that are sampled according to the underlying probability distribution of the interaction. It does this analytically using the exact formulae for your given Lagrangian, and it integrates this using Monte Carlo. If we want to accelerate MadGraph, we should probably first take a look at where do we spend all of this compute. And given what I've already said, it's probably not all that surprising that the entire runtime is spent in helicity amplitudes. Here I have a flame graph depicting the timeline, more or less, for the process GG going to TT bar GG. This is not a simple process, but it's far from the most convoluted process we might want to try to analyze. And here I've highlighted this so-called matrix function, which is just the wrapper for the helicity amplitudes. We see that even here, by far not the most complex process we want to actually evaluate, we're already spending 96% of the runtime in the helicity amplitudes. Going back to MadEvent itself and justifying why this is the case, MadEvent has a triple purpose. You want to Monte Carlo integrate the cross-section of the process. You want to determine the underlying distribution of the process, giving us a so-called grid. And then you want to sample this grid to get unweighted events, which are essentially sampled with respect to how often you would see them in your detector. All of these purposes, for all of these purposes, we call helicity amplitudes. And one more note before we get into CUDACPP is that at leading order, helicity amplitudes are identical across phase space. So for this process I've shown you here, we're spending 96% of the total runtime evaluating the exact same function, just with different input values. That brings us to the CUDACPP plugin that we've developed. But before we actually talk about the plugin itself, I just want to take a step back and look at the types of architectures we're targeting. First off, we have vector CPUs or SIMD machines, meaning single instructions on multiple data, and how these differ from what you might imagine when you think of a processor where you have one input datum and one input instruction. You run the instruction on the datum to get a modified result, is that, well, a lot of the time we're just going to be running the same operation on a lot of data anyway. So why don't we just increase the register of what we're giving to the processing unit? Essentially, you're saying that, okay, instead of one piece of datum, you take 2 or 4 or 8 or whatever, and then you set up your instruction at the hardware level so that it will split this operation such that it acts identically across these blocks. Doing so gives you, assuming that your program is already set up for this, essentially a free n-fold acceleration. The other type of machine we're targeting are SIMT machines, typically GPUs. And these differ from SIMD machines, not so much how you should think about them, but in the way they're constructed. Whereas a SIMD machine has a single processor working on many data, in a SIMT machine, you just say that, well, we can just manufacture a bunch of easier, simpler processors, and then put them all in a row and say that, hey, you guys do the same thing at the same time. So instead of having a single processor running one operation on n data, you have n threads acting on n data, one piece each. But because these processes have been simplified so much, you can just put thousands of them in a row and thus get, if your problem is set up correctly, quite a bit of speed up. I'm not going to talk too much about thread divergence here because it's actually irrelevant for our work, but in general, it's something to keep in mind when you're accelerating software. So going back to MadGraph, just to remind you, we're spending all of our runtime in helicity amplitudes. Helicity amplitudes are identical across phase space. They seem to be a pretty good point for data parallelism. So the practical idea we had going in and what we have done is essentially maximize the acceleration while minimizing the amount of source code modification. We want to have as little, as few changes to the MadGraph project itself. And how to get this done is to essentially maintain the Mad event code, the Fortran base, and then have a separate interface calling, when Mad event needs to evaluate helicity amplitudes, calling a interface to our CUDACPP plugin to evaluate these helicity amplitudes. Of course, this involves some upstream changes and a loss of work within these amplitudes. But in general, this is a way to really push on that one piece of data parallelism, which we know we can really make use of. Now, this has been done, and seeing it written down like this makes it look easy, but of course, that's not the case. I want to talk about two major hurdles that we faced in this work. Of course, there are many more, but these are really fundamentally the two things to keep in mind while accelerating software, particularly HEP software. The first one is multi-event APIs, and the second one is data locality. By multi-event APIs, we mean that a lot of code is written under the assumption of sequentiality, that you will only be running one event at a time. So you run code, call event thing, run code, call event thing, etc., etc. You really need to make sure that your program can be like, oh, instead of just saying, hey, I'm going to get one event here, I need to be ready to get n events, which could be any number. And then the sequential version of this program will just be the specific version where we have n equal to 1. The second and more devious of these devils is data locality. Like a lot of large old code, Mad event is not exactly clear on what data it needs to access. We use a lot of common blocks, we use a lot of public data, we use a lot of statics and similar. And this means that as a stranger coming in, the actual data dependency of the code is completely incomprehensible. This makes it difficult to impossible to ensure both data safety and the actual data access that you need within your interface when you're writing some accelerated code. And although we have already done this work for leading order event generation in MadGraph, this is an issue that still remains for us specifically within MadGraph, but also in general within HEP software. So I just want to illustrate that this is what you need to keep in mind, both when you're rewriting old code, but also if you're writing something new. If you want to be able to make use of data parallelism, you should keep this in mind. Make sure that you have a general structure where you can parallelize any given function, where you make sure that each function knows exactly which data it needs to access and output. But yeah, so that's the work we've done. And with the work we've done out of the way, I'm going to show you a few small results. Now, again, Jin will really go over this more structurally, so I'm just going to show you some highlights, and particularly I'm going to refer to the theoretical speed up we might see from some mathematical analysis. First off, here is another flame graph. And actually, it's the exact same flame graph as before, except this time, the helicity amplitudes have been offloaded to a GPU. So here we're running our Mad event, single-threaded, but all of the helicity amplitudes are running on a NVIDIA A100. And what we can see here is that that thing I've highlighted, that's the helicity amplitudes. That used to take 96% of the runtime. It's now down to 1. But wait, if we've taken what took the entire runtime and we've completely eliminated it, then our program should be instantaneous, right? Not so fast. Here we get into how we actually define acceleration. I'm going to be referring to Amdahl's law. There are other alternative ways to analyze acceleration, Gustafsson's law is the prime other example, but I'm using Amdahl because it is quite intuitive to understand and because it's the number that most people usually refer to. So what does Amdahl's law actually say? It says that for a program for a sequential program with a runtime of 1, if you parallelize a fraction p of this program, then what you will actually be limited by in the end is the fraction you did not parallelize. As a quick example, if you have a program where you parallelize 90% of the code, 90% of the runtime to be specific, and you have infinite parallelism, so you have a machine with an infinite number of processes, then you can never gain acceleration above a factor 10 because you're still limited by that 10% that is still completely sequential. With that in mind, let's actually look at some numbers. I just want to say that these numbers are actually a bit old at this point. They're from last year, and there have been changes to the master branch of the plugin since then. But these changes have not had any major impact on performance, rather just being bug fixes and such. So the numbers, although old, are still representative. Going from top to bottom, we see increasing process complexity. And on the left-hand side, I've highlighted total runtime and total Amdahlian acceleration. Then on the right-hand side, I've highlighted the acceleration within the amplitudes themselves. And what we see is that although the acceleration within the amplitudes decreases as we increase the process complexity, because it's still accelerated by such a huge factor, always being over 2 orders of magnitude, the total acceleration still grows with process complexity. That's quite nice, I would say. But what's even more nice, at least from an analytic point of view, is that remember that process I've already talked about a bunch of times, GG going to TT bar GG? 96.1% of the runtime was spent in helicity amplitudes. By Amdahl's law, the maximal acceleration we can get here is 25.6 times. If you look at this table, you'll notice that for the middle process, GT going to TT bar GG, our acceleration factor is 24.9. I would say that we're doing all right. But of course, this is an unfair comparison. We can make some Amdahlien analysis out of this and say that, woo, we did accelerate as much as we could. But it's not a fair comparison because we're comparing single-threaded runs to single-threaded runs with a beast of a monster doing the biggest part of the calculation. So let's actually look at vector CPUs, where we do have a far fairer comparison. Because here, the only thing we're not changing machines. We're using the exact same machine, but we're changing the level of vectorization in our code. So as I mentioned, in a vector CPU, you can just increase the vector register that your processor will act on. And here we've done just that test, same process as before, going from no vectorization to 2-fold vectorization, 4-fold, and 8-fold. And on the right-hand side, I've highlighted the acceleration within the amplitudes themselves. And what we see there is that, well, for a 2-fold acceleration, we get exactly a factor 2 speed up. For a 4-fold acceleration, we get a bit above a factor 4 speed up. And for an 8-fold vectorization, we get just above a factor 8 acceleration. Of course, there are statistics to this, and there have been some small optimizations in the code itself that allows us to go above the theoretical maximum. But what I really think should be highlighted here is the fact that we have reached the theoretical maximal acceleration given the part that we've actually parallelized. So, wrapping up this part, wrapping up the part where I talk about what we've already done, I just really want to say, you can go and check this out right now. As of last month, the CUDACPP plugin has an official 1.0 release. I have a link here to our quick start guide on our GitHub wiki. And this version of the plugin is completely compatible with the latest version of the upstream MadGraph project, 3.6.0. And we have support for vector CPUs, as well as NVIDIA and AMD GPUs. And we have support for, at the very least, each UFO model that we have tested. So as far as we're aware, we've gotten what we wanted out of this. Basically, I just want to say, test this out, check it out, both literally and figuratively, and feel free to reach out to us either by submitting a GitHub issue or just contacting us directly if you're wondering about anything, or you have some issues, or you want to maybe add to it in your own way. I don't know. Now, I could end the talk right here, but I'm not gonna, because I'm selfish like that. And really, what I want to stress here is that although we have gotten the thing that we originally set out to do done, we are not done. We have several parts of this project that we're still working on and looking to integrate in the both near and far future. And these can roughly be split into two different categories, one being optimization of what we already have, and the other being feature extension, where we add new possibilities of what to do with the plugin. Going into the first part of optimization, we're facing several of what I like to call magnitude issues. These come in three different forms. The first one is the fact that for very complex processes, the bottleneck is still the amplitudes. For even running on an NVIDIA A100 for, I think I showed it in the table before, but the majority of the runtime, by a small margin, sure, but still, is spent within the amplitudes themselves. So optimization there should still give us some measurable speed up. However, more significantly is the fact that the code size grows with process complexity, and the process complexity scales, as mentioned, factorially. Particularly, the way our code is currently structured, all of the process-specific information is stored within a single file. So for complex processes, the one I've illustrated here, this file can be over 30,000 lines of code. It's not exactly nice to the compiler to tell it to try to optimize that. We're working on this. We're trying to split up files, trying to simplify compilation chains and such. We're looking into it, is really what I want to say here. Because what I'm personally more interested in is the second point, because it's closer to physics and I'm a theorist. Yes, laugh at me, haha. Where we're going from event parallelism to helicity parallelism. Now, what is the justification for this for our work, not in general, but for us? And it's actually quite simple. Modern HPC-grade GPUs are really big machines. They have tens of thousands of threads running at once. And in order to actually reach maximal throughput, you need to fill these machines up. And you need to overcome all of the loss that you gain from the latency between host and device. So one way to gain even more is to just increase the level of parallelism. And that is the idea here. And I have a small diagram here showing the idea. This is work in progress. So numbers are not to be quoted, but the idea is nevertheless quite sound, which is that, as mentioned, what we did previously, well, what we're doing at the moment is to just have one thread on the GPU evaluate every helicity for one event. But we can just go from this to instead saying that one thread on the GPU should evaluate one helicity for one event. Of course, such a change means that you will be doing more I/O between the host and the device. So we expect to see some reduction in maximal throughput doing this. However, by also including a smarter memory access way using CUDA streams, we actually find that the total effect when we've done this change and included CUDA streams on the maximal throughput is negligible. However, the actual number of events you need to generate at once to reach this maximal throughput is reduced by 2 orders of magnitude. You're going from having to generate over 100,000 events at once to even see the maximal throughput to needing to generate like 1,000. Of course, this is process specific and will vary very much depending on the physics, but it does still showcase that we can really make better use of these machines in the sense that we do not just need to, increase the data size. Instead, we can just be like, oh, increase the level of parallelism. Now, going on to the new features that we're working on at the moment. The first one here is with respect to matrix element reweighing. Why would we consider that? Well, justification is quite simple. As I mentioned, we've gotten to the point where what used to be the bottleneck is now negligible. So we have these really fast vector routines, but we're dominated, or at the very least clogged up, by all of the surrounding integration. For reweighing, we only really care about the amplitudes themselves. So what we've done is we've developed an extension to the CUDACPP plugin called T-Rex, which is an override to the native reweighing functionality of MadGraph using our own internally developed libraries to do LEG file IO and reweighing calls to call our vectorized routines. Again, work in progress, but we do have some plots here, and these are actually not representative because they were made with the previous version of the code, so hopefully it should look even better now. But even here, what we can see is that going from left to right on both of these plots, we're increasing complexity, and going from the bottom to the top, we're increasing the number of parameters that we're reweighing to. And as we increase these numbers, we're achieving quite significant acceleration also here. Finally, the elephant in the room, the white whale. Everything I've presented so far has been for leading order. But we are very much working on vectorizing also next to leading order event generation. The algorithm is still in development, so we aren't able to run it and get results quite yet. But we can estimate what we stand to gain from this work under a couple of assumptions. Basically, if we maintain the structure from the CUDACPP plugin of event level parallelism, where we vectorize the helicity amplitudes, then we can note that, furthermore, in MadGraph at least, using our evaluation routines, the NLO amplitudes can be split into 4 parts: the Born amplitude, the real emission amplitude, the loop amplitude, and the counter terms. Save the loops, all of these are tree level. And tree level amplitudes are exactly what we've already vectorized for leading order event generation within CUDACPP. So we can immediately recycle that work, of course, with some more work to deal with the subtleties of the NLO, but to immediately gain that level of acceleration within these types of amplitudes. I also want to mention that although it's not our work, we actually have external collaborators at Argonne National Lab looking into also vectorizing loop integral libraries. To try to convince you that this is a fair workflow, here I have a runtime profile of NLO event generation within MadGraph. Again, going from left to right, we're increasing process complexity. And here I am only showing the fraction of runtime spent in different types of amplitude calls. There are 2 things to note here to justify our work plan. The first is that in all of these cases, even the simplest case, the main portion of runtime is still spent in amplitude evaluation. We're still dominated by helicity amplitudes. Furthermore, looking at the idea of just reusing the tree level amplitudes from the CUDACPP plugin, I would like to point out that for all of these processes, loop amplitudes are subdominant. Of the amplitudes, which take up the majority of the runtime, they always take up the least amount of the runtime. So although we're not expecting to see quite a significant speed up in NLO using this work plan as we did for leading order, we should still see something quite significant. Now, with that, my throat is starting to give out, so let me try to wrap up. Just to summarize what I've already said, after several years of hard work, CUDACPP, the MadGraph plugin, is finally available. It's available on our GitHub. We have a wiki with a quick start guide. The link is available on the slides, which you can find on the Indica page, or if you're looking at this on YouTube, maybe we'll include it in the description. What do I know? We see that we have quite considerable speed up, at least in an internal testbed situation. But Jin will talk about this more extensively in just a couple of minutes. And finally, again, I want to hammer home that we are not done. We are still working on this. We're making what we already have better, and we're trying to extend the functionality of our code. Hopefully, within the near future, we can say that, yeah, we can do leading order reweighing. Yeah, we can do NLO event generation. Yeah, we can do, I don't know what else we might want to do. The point is, there is still work to be done ahead of us, and we are looking to do it. So to wrap up, I would like to give a couple of thanks. First off, I would like to thank SAPTA for the nice invitation to let me speak here. Secondly, I would like to thank my amazing team for the work that we put into this. I would like to thank my supervisors, Stefan Heuser, as well as Robert Schörfbeck. And finally, and most importantly, I would like to thank you all, my wonderful audience, for listening. Thank you.
Thanks, Zenny. Okay, excellent. That was very informative, and it's nice to see how this work has advanced over the last couple of years. But I think we can now open up the floor to questions, just to abuse your throat a little bit more. So if anyone on Zoom would like to ask a question, just raise your hand. And if you're in the room, just wave at me, and there are actually microphones on the desks. So it's quite easy to make yourself heard in this room. It's got very dark as well, hasn't it?
Yeah,
it's to switch the lights on.
I switched slides,
Somehow.
that's why. I want to escape here so I can see if anyone's written in the Zoom chat.
Yeah, I'm looking at it here. So
okay.
Okay, maybe I'll start then.
Yeah.
So you mentioned NLO.
Yeah.
And I think if you look at the physics program for high luminosity, that is actually the prize.
Yes.
Because that's the place where we probably have to go to get the theoretical accuracy that we need. And we know that it is a huge bottleneck for us. So what's your estimation in terms of the amount of time it's going to take to get NLO event generation running in this, using all that you've learned from leading order?
Well, let's put it like this. I'm expected to finish my PhD next year.
So you'll be done by then?
We'll see. But we do have an almost working prototype of a simulated vectorized version of the NLO code within MadGraph. And actually getting that working entirely, and then, of course, actually making sure that it's working not just for fixed order calculations, but also for event generation. Mm-hmm. That's probably short-term work within the next couple of months or so. However, then, of course, it's the moving on to actual vectorized routines for the helicity amplitudes. And that is more significant work. As mentioned, we can recycle a lot of what we already have for leading order, but there might nevertheless be complications that are somewhat unexpected. I cannot give you an exact idea of that, but I would say that I'm hoping to, at the very least, have let's say an alpha release of a working code by the time I do my defense.
Okay, sounds good. So you're ambitious in terms of the timescale. Okay, thanks. Questions from Zoom, from the room? Comments?
It's more like want to ask your opinion. So thank you for the talk. It was really, really great. So my question is, do you think the experience that has been gained during all this process of porting MadGraph to GPU could be also beneficial for other event generators? What do you see in the future, like in this field? Because MadGraph is just the first event generators from the theory to the events. Then you have, of course, like generators like PITIA for showerings and also detector simulations and so on. What do you think?
The issue there is, of course, that the benefit we have for helicity amplitudes is that we are evaluating the exact same function in lockstep for every phase space point. That no longer holds true when we're going to more approximative schemes, going to showering, going to detector simulation. So there we have less benefit to see from lockstep processing. But nevertheless, we can still keep parallelism in mind, where as long as we remember that these beastly machines that we now have can chug out operations so much faster than what we had before, it might be okay to start throwing away some data, knowing that we might be doing erroneous operations if we, for example, run some, let's say a detector simulation where we just have particles advancing in time, and we do stochastic branching at each time step. If we say that, okay, we might bias ourselves if we say that every particle should do this branching, we can still do it and then just say that, well, to make sure that we aren't biasing ourselves, we're just discarding, or at the very least, saving these results separately from what we're actually using, and then saying that, oh, well, if we do something with the opposite, then we can then repurpose this remaining data from before, combine them in some sense, and gain from there. I would say that the experience we've gotten here definitely helps for mindset towards parallel programming. It might not be immediately applicable to other aspects of HEP software, in the sense that you cannot use the exact same methodology, but the ideas behind it are nevertheless quite useful, I think.
Thanks.
Thank you. I think we gained valuable experience from all of this work. We have a question from Charles. You want to just go ahead, Charles? I think we can hear you here.
Hi. Thanks for a really interesting talk. So from what I understand, one of the issues with NLO and NNLO calculations is they require higher than double precision calculations. Can you say anything about, quad precision and beyond, and how one would deal with or avoid using those types of calculations because they're not terribly well supported on GPU?
Yes, absolutely. So specifically, where we do end up needing higher precision is mostly within loop integrals, where we need to ensure stability of the actual integral, and it will be extremely dependent on the exact phase space point you're at. So you might face instability if you're using lower order precisions. How we are facing this in this project is, of course, to say that, well, we'll hold off on the loops and just say that we're trying to optimize everything else. We're trying to get everything else as fast as possible, and then the loop would be a new bottleneck. But I can also say that at the very least at NLO, within MadGraph, most of the time we do not actually need quad precision for the loop integration. Sometimes we will, of course, need it, particularly depending on the process. But if we say that, okay, we can run these on an HPC grade GPU most of the time, and then the times where it ends up being unstable, we just run it back on the host. We can still gain quite a bit of speed up from that. But it should also be pointed out that GPU vendors are catering to profit incentive. And at the moment, profit incentive means machine learning, particularly LLMs. The thing with machine learning is that, well, you want to do an awful lot of matrix algebra, but you don't really need all that much precision. So a lot of GPU vendors, and I've actually gotten into conflict with people at NVIDIA over this, are, I'm not going to say removing support for higher precision on GPUs, even double precision, but they are less invested in it. But I can say that at the very least, Stefan Reusser, my supervisor here, is very interested in software solutions for higher order precisions. So he's looking into, well, not him personally, but he's looking into having someone look into the possibility of simulating higher order precision efficiently on lower precision machines. But of course, then we have alternative architectures and hardware that are coming, that are really starting to come into the limelight now, where you can actually, well, where we might hope to see higher order precision more easily accessible, even on accelerated devices. So I would say that right now, just looking at modern market GPUs, it's not looking all that good, but we should still be hopeful. It's not a lost cause yet.
Thank you very much. And yeah, let's say a last quick question from James.
Yeah, hi, thanks for the really nice talk. Can you hear me okay?
Yes.
Yep. So I'm guessing all of these, I think you said it, in fact, all these benchmarks have been done on a kind of on test machines, but I'm wondering, do you have any plans, or you would like other people to try this sort of more in the wild on a larger HPC systems and this kind of thing, to see how this works when it's not in test conditions?
I think that would actually be really nice if someone did. At the moment, our machinery does not support multi-GPU nodes, as far as I'm aware. So that might be a bit restrictive. But in general, I think it would be excellent if people had the opportunity to just test it out. Of course, Jin will give a talk about the testing within the CMS computing structure, just in, I would say, 1.5 minutes. But anyone who feels like they might want to test this out, absolutely.
Okay, thank you. Thanks.
Yeah.
Right, thanks for the question, James, and thank you very much, Zenny, for the really interesting talk and the nice discussion. Let's find the Zoom window. Wait, where is it? Wait, I want to stop screen sharing. That's what I want to do. Jin, do you want to take over the screen share?
Yeah, okay. Can you hear me?
We can hear you very well, yes.
Okay, and now I share my slides.
Okay, and I'm just going to make this full screen in the room, and yeah, it's looking pretty good, so I'll let you take it away.
Okay, thank you. I'm Jin and I'm a PhD student in Seoul National University and working in Generator Group and CMS. And first of all, I want to thank Zenny for such a nice talk for the theoretical side. And today I'm gonna talk about the first benchmark with MedGraph for GPU in CMS. Okay, so I want to start a brief introduction with about some respects in high-lumi LHC. We have successfully measured many of the standard model properties in run 2 and run 3. Still, run 3 is running, but we can look more what we are missing with extra precisions. For example, like measurement of a very small cross-section standard model processes such as like vector boson scatterings, or like many Higgs, like two di-Higgs production cross-sections, or like some with extra TT Higgs or BB Higgs. And also maybe, I'm not sure, it could be possible in high-lumi LHC, but about the triplex coupling and any other BSCMs that with very small cross-sections, like order of a single femtobarn or like 100 autobarn, this cannot be reached. It depends on the background, but it cannot be reached in the current run 2 or run 3 luminosity. So it goes to the high-lumi LHC. It will start to run in mid of 2030. And what we are expecting is we will gather about 3,000 inverse femtobarn or up to 4,000 inverse femtobarn of the integrated luminosity in this period. Okay, so to gather this kind of integrated luminosity, we will increase the instantaneous luminosity about 3 or 4 times. And for MC production side, it requires about 10 to 100, order of 10 to 100 billion events to be simulated. So let's focus on the computing side. In LHC, we are expecting to purchase about 10 to 20% more computing resources every year. But as you can see in the plots on the right side, it would not match our need if we only update the hardware side. So we should accelerate softwares, and it is a very essential part for the computing in the next phase. The good thing about the technology itself is most of the software for run 2 and almost all of the run 3 are based on SISD, which means we often use single core execution, or the parallelism is done in thread level. But as Zenny explained, there are many advancements in SIMD or SIMT with better CPUs and GPUs. So many of the softwares can be accelerated with this kind of scheme. And the very good thing is about the vector CPUs itself. About 80% of the computing in LHC supports AVX2 vectorization scheme, so we don't have to purchase any budget to use this technology. And also, of course, additional powerful source of accelerating is GPU. Let's dig a bit more into the Monte Carlo sample production in CMS itself. I want to highlight some ongoing updates we are doing. About 50% of the computing resources are expected to be allocated to Monte Carlo sample production itself. So in CMS, we often divide this into 3 steps. The first is gen, which means like generator. And of course, the major project for accelerating here is a MEG for GPU. And the second part is the simulation, which is the detector simulation based on Gen 4. There are some analysis with the GPU ported Gen 4 in CMS workflow, and also people are trying to use machine learning based fast simulation to accelerate the detector simulation. And the most time consuming part is the reconstruction, and the most time consuming part of the reconstruction itself is mostly track reconstruction. So people are trying to vectorize these common filter algorithms or for it in the GPU, and some machine learning based particle flow algorithms. Of course, it's not primarily aimed to speed up, but still we can get some achievements. And there are also another approach using the end-to-end machine learning based fast sim. It's very cool. It just take the matrix element LHE files as an input, and the final output will be some format that we can do analysis like mini EUD or nano EUD. So the thing is that this replacing full sim with fast sim or like PF reconstruction algorithms are often developed within CMS, but like MatGraph or generators or Gen 4, these kind of technology, this kind of softwares are treated as an external libraries in CMS, and they should have updated by the authors. And often the generator is the starting point of the sample production, and usually in CMS, people are not trying to accelerate it within the CMS workflow. So MatGraph for GPU is the first program that we can test in generator side within the CMS workflow. A bit more why we try to accelerate with the MatGraph, test with the MatGraph. First of all, because there is no or less developed generators that we can test in GPUs or the current CPUs, but still, MatGraph is a generator for like mass production. About 1/3 of the event simulations done in MatGraph for run 2. And the MatGraph is a generator for first search. Most of the BSM searches are requested with leading order MatGraph. About 2/3 of the samples requested in run 2. And MatGraph for GPU in CMS workflow, it is the most common background. Most common backgrounds like trillions or TT-bars are generated with MatGraph or AMC at NLO. Let's say in practical numbers, about 100 million events in run 2 and run 3, like trillion for the trillion sample in 2018, about 100 million events have been generated. So for testing the speedups in high-learning LHC, it is the right time to test its speedups for preparing mass production. A bit more about the sample production in CMS. I already told that it can be divided into gen, sim, reco steps. Let's just focus on the generator side. In CMS, we use grid packs. It is a package that encapsulates the pre-computed matrix elements and other scripts that we don't have to recalculate in other machines when we try to make the events. So these grid packs are distributed to various computing centers like tier 1 or tier 2. And so we use this to generate the LHE events. And for the practical timing, grid path production just have to do only once. So it is often shorter than event generation. Like I already told you that for Julia, we need about million or billion of events, but we only have to evaluate the grid paths for once. But still, heavy grid paths with multiple jets, like Julia plus 4 jet with leading order, or Julia plus 2 jets with next leading order, it takes a few days or a few weeks to produce. Okay, so let's move on to the actual experiment that we have done. We are starting to test this MATLAB for GPU with the most basic and common backgrounds in CMS. We are testing Drelian and top-core pair production. Drelian is really nice. We really use it very much for the common background. And in CMS, we do not require any external dependencies. So it allows we use all the CMS central cards for production. For TT bar, actually it depends on math spin in when we decay W. And math spin is not supported by the MATLAB for GPU yet, but it is the most speed up observed by the MATLAB team. So we want to recheck its improvement in the CMS sample production setup. So for the experiment, we are following the CMS gen production steps. The experiments and the numbers are divided into grid path production and event generation. So basically, we are comparing timing by switching backends. Here, I just denoted Fortran, CPP, and CUDA. It is just the name of the parameter in the run card called CUDACPP backend. Fortran is just a legacy plugin that used in the previous MATLAB versions. For CPP, it just denotes the vectorized CPUs with AVX2 supports, and CUDA, of course, it's GPUs. To scrutinize more deeply, we are studying with JetBand fashion and inclusive. For the JetBand ones, as the external jets, with more external jets, the complexity increase, so we can check the speedups and overlaps with respect to this increasing complexity. For inclusive study, it is the real physics that we are interested in, so we're looking at it. For the testing environments, I don't want to go through all the details about the hardwares we are using, starting from AMD to Intel CPUs and A100 GPUs, H100 GPUs. But for software, it is really important to isolate the test environment to compare the speeds. So we are using the HD Condor, but the fact is that CPUs and GPUs are exclusive. They are managed by the Condor system itself, but memory and I/O bandwidth might not be shared. It cannot be managed by the Condor. So if the events is located in the same machine, then they should share the memory and I/O. For the OS, we are using EL8-based singularity image to synchronize within all the machines. We have used the latest MATLAB version with the developing version of the MATLAB for GPU. And all the codes are integrated into centralized CMS generator code. With some modification to make it run smoothly on our codes. We have accelerated with the CPUs in AVX2 vectorization scheme and also GPUs using the NVIDIA CUDA GPUs, NVIDIA GPUs. Theoretically, in AVX2 scheme with double precision that requires for the leading order production, we can achieve up to 4 speedups. So 4 speedups. A bit more about the integration. Development of generators are managed by authors, so we are not touching it. For the MATLAB, it can be smoothly integrated into the CMS grid workflow. Actually, what we have to do is just call the MATLAB for GPU plugin named MATEvent GPU. And after that, we can switch the parameter in the one card called CUDACPP backend. So we change this parameter from Fortran to CPP to CUDA. At the timing of testing, there was no actually the official release of the CUDACPP plugin, so we have used the developing version since somewhere in this August. But still now in this October, the first version of this project have been launched out. So please check this project in the link here. Okay, so let's see how the GridPack production have accelerated. Before we move on to the actual numbers, I want to say about the difference in the plugins itself. There are some impacts of different plugins from many diagram processes called parton grouping. So basically, for the math event, the processes are grouped with group partners are treated within the same subprocesses. But the newly developed math event GPU for, I think it's a debugging purpose, but this kind of feature has not been implemented. So if we just try to generate Drellian plus 4 jets without this implemented group parton grouping, then the number of diagrams and subprocesses are just will be a lot. So because of the timing issue, we are trying to simplify the parton definition for like multi-jet Drellians, especially for the Drellian plus 4 jet and Drellian plus up to 4 jets. Here we simplified means the parton and jets are UU balloon, and leptons to be just electrons and positrons. And one thing, two things I want to emphasize on. This have large impact on GridPack production, but it should not affect in event generation. And the next thing is I know that authors are really working hard to implement this parton grouping in the next version of the CUDACPP. So complexity overview for the Drellian plus no jets, the number of diagrams is 30, and there are 15 subprocesses. But when we go to Drellian plus 4 jets, the complexity grows really much. There's about 400,000 diagrams with about 1,500 processes. But after we simplify it, the number of diagrams reduced to 10,000, and the subprocesses we want to optimize reduced to 13. For TT bar, the number of diagrams and processes are much spare compared to Drellian. So with this higher multiplicity, the system should handle a great number of processes. So in this case, other constant overheads such as compilation or after auto calculation, the combining results or some bottlenecks in some subprocesses, this can reduce the speed up, which mostly impacts in Drellian. So this page is the actual numbers we have got, or we have used various HPC machines to produce these numbers. So we have to normalize the numbers with, and the way we normalize is to normalize with the how many math events we have executed in parallel. For the low multiplicity Drellian or TT bar, there are not much improvement we can observe. Actually, the matrix element calculation itself is not really a bottleneck in these cases, but for high multiplicity processes like Drellian plus 3 jet, Drellian plus 4 jet, or TT plus 3 jet, there are huge improvements. For example, in Drellian plus 4 jets, we have achieved like ×3 in CPP AVX2 and about 50 times faster execution for producing grid packs using GPUs. For TT bar, it's outstanding. If we use factorized CPUs, then we have achieved 3.5 times faster. And with GPUs, we have achieved 90 times faster, which is almost the number that we have seen by the MATGRAPH benchmark in TT plus glue. Yeah. And what we actually interested in is the inclusive study. For the GRIPAC side, actually the most time-consuming part is the computing the metric sound calculation in high multiplicity processes. So the timing does not differ a lot with Dragon plus 4-jet or TT plus 3-jets. Comparing the Fortran and CPP IVX2 supports, we can achieve like ×3 speedups, and for CUDA, about 45 times faster for Dragon and about 85 times faster for TT bar. But still, this is comparing with normalized number of the meta events execution in parallel. In real world, often HPCs with CPU only HPCs often have a lot of CPUs. Like, let's say in NERSC CPU only machine, we can execute with 256 meta events in parallel if the memory accepts. So it allows more submission in CPU, more submission than heterogeneous CPU plus GPU architectures. So to get some real life numbers, like in TT bar 3-jets, the dominant process is glue to TT glue. It requires about 6 gigabytes of memory in 800 GPU, which means inside of 40 gigabytes of 800 GPUs, we only can run 6 meta events in parallel. So these speedups might be can be seen like order of 100 times faster execution for NVIDIA GPUs, but actually in real world it would result in overall speedup up to order of 10 for CUDA, but still it's a lot. And let's move on to the event generation side. This is really simple. After we produce the grid pack, then we can execute the event generation with arbitrary number of events. So we just scan how much time it will be caused with increasing number of events using a single core or single meta event. Again, I'm not going through the hardware side. So we run each test 8 times in parallel, and we computed mean and standard deviation to avoid the fluctuation in single run thread running. So in the plots here, the x-axis is the number of events, and the y-axis is the actual time we have observed. And again, overhead might be caused due to sharing memory and I/O within the same HT control node. And especially in LX Plus, there are not many 800 GPU nodes, so usually they share the single GPUs, so it might cause overhead and not might show a linear trend in GPUs. I just trying to show 2 results in the inclusive ones that we are interested in. The left plot is the trillion and the right plot is the TT bar. We have observed over improvements in both trillion and TT bar, even if it's inclusive, and approximately about 1.5 times faster for vectorized CPU supports and about 7 times faster for CUDA compared to Fortran. So it leads to me the summary. I have shown the first benchmark of the MATLAB for GPU integrate into CMS workflow. It is a starting point. In high-Lumi LHC, we will require about order of 10 to 100 billion events to be produced. And as the MATLAB is a central MC sample, central to the CMS MC sample production, it generates about 1/3 of events and 2/3 of requested sample during run-2. So for the benchmark, we have tested the most common processes for the start, the Dragon and TT bar. For the GridPack production, we have achieved about 3 times faster for CPP AVX2 and up to 90% depending on the processes with CUDA-based NVIDIA GPUs. For the event generation, we have observed about 1.5 improvements for AVX2 vectorized CPUs and about 7 times faster for CUDA when we try to generate 100,000 events. So this is the results I've got so far. And yes, and this is the end from my side. And so feel free to ask any questions.
Thank you so much, Jin. Okay, great. So yeah, we can certainly open to questions for people in the room or people on Zoom. You know the drill. You know where the hand button is on Zoom. I guess I have one comment and a question, so I'll just go first to get things started. The comment actually is that in some ways, I'm kind of more impressed by the results for AVX2, and I'll tell you why. Because this is performance that we're just letting fall on the floor every single day, because these CPUs are there already. And we know that the availability of GPUs on the grid is still a bit shaky. We want to use it when we can, but the fact that you get these big speed ups by taking advantage of the vector registers, I think this is fantastic. My question is, based on the 3 backends, did you do a validation run just to check that you really got the same results from each of the different backends?
For the current stage, we are trying to see how the speed changes within these changing backends, and the physics validation itself, like distributions or cross sections, we are actually looking at the cross sections, but the actual distributions we have not been started to validate yet, and it's the job we have to do for the next iteration.
Okay, cool. So you've looked at it a bit, but work in progress there then. Yeah, thanks. Okay.
Just a follow-up comment on your vector instructions on CPUs. There was a study, it is already 1 or 2 years old, by Andrea Jabba, where he looked at the WCG compute resources, and he found that at the time, I think 80 or 85% of the computers out there for WCG are AVX2 or better. So I completely agree with you on your statement.
Thanks, Stefan. Next question from Sapta.
Thanks. Sorry, this may be a bit of a leading question, but thanks a lot, Jin, and also Zenny, for the really excellent set of talks. I was just curious, Jin, if you could comment on, the production readiness. I know that we need to also, the computing improvements are hand in hand with physics validation, but say we have, the physics validation is done, say, tomorrow, then how fast can we have the GPU version of MatGraph in production? Your thoughts on that. How are we in terms of mass production with this version of MatGraph?
For the vectorized CPU side, it's really doesn't matter. Anyway, not only the vectorized CPUs and also the GPUs. Let's see here. The only thing that MatGraph had to do is produce LHE events. That is done by all of the backends then. So actually for the vectorized CPUs, it just can be ported to any chains of the production. So it doesn't matter. And for GPUs, of course, it would be great if there's also GPU supports for the steps afterward. Like I don't think the parallel showers are implemented, but still there are efforts to work in simulation side for the GPUs. And in my just simple thought, in Halloumi LHC, the CPU workload and GPU workload should be divided so we can 100% use our resources. But for the production side, the only thing we have to do is produce the LHC files, and we have tested that it can be worked in the GPU workload.
Thank you. So there are no technical issues as such. It's more of getting all the parts together.
Yes.
Thank you.
Right, thanks for the question, Sapta, and the answer. James, you're next.
Yes, again, thanks for the really nice talk. So this is just a workflow question. If I understand correctly, the LHE files are produced separately from all the rest of the event generation steps, right? So if I understand right, the LHE files are made here, and then if, let's say, you were using some big HPC, they would be offloaded, and then all the other steps involving Pythia and the other things which aren't yet migrated to GPUs would run on the normal grid resources. Is that a correct statement, or?
That could be possible, but not always, because the thing is that we often use grid text and we start to generate LHE start from the bottom. So your workload is possible. We can generate a huge amount of the LHE files in certain HPCs and then go to the hydrogenation level. Then that requires always recalculate the matrix element in each HPCs.
Okay. Yeah, maybe I'm not quite sure. So just imagining how this would be used for real, you know, on some resources that had GPUs. Would the final output of this have to you would have to write some file to disk, and then it would be read by subsequent steps, or is it all done? I'm just trying to figure out how the choreography would be done on the grid or on an HPC or something. If I look at this diagram, for example, so the red box, which you've got, which is here, not all of this red box is going to be running in the setup that you've described in this talk, right? If I understand correctly,
yes.
Or maybe I'm wrong.
I think, not I think, yeah. The thing is that LHE files should be created, but how we manage it is that for the entire gen step, the LHE file can be created by the grid packs, and then it just goes directly to the hydrogenation using like Pythia or Harwig. But the case in rewriting the LHE file in the disk and then moving to some other machines to do hydrogenation and going to the next steps, it's also possible. There are two ways to do that, but for the mass production side, we usually produce LHE files and hydrogenation at once. Would it be enough?
Liz, did you want to make a comment on this point specifically?
Yes, I wanted to be clear that what he just said, that the first scenario is what we use in the mass production for run 3 and run 2. But one of the things we can do is use process isolation. So in the gen step, we for a lot of these generators, we fork off a couple of gen processes that then feed their results back into the next step when the module goes from module 1 to module 2, you know, from the gen module into the hadronization and simulation.
Okay, that's great. So given the appropriate mix of CPUs and GPUs on wherever this was being run, you could in principle do all of the steps in this red box in the same, okay, in quotes, process. It wouldn't be the same process, but
yes,
you wouldn't have to write everything to LHE files on disk. Okay, that's very nice.
Right.
Yeah, thank you.
Yeah, thanks for the question, James. Charles, you're next.
This is also a bit of a workflow question. So when you send out a job to the grid, you might not necessarily know exactly what hardware you're going to end up on. Is MadGraph at this point smart enough to realize, oh, look, I have this hardware available. I have AVX2, or I have a GPU with 80 gigabytes of memory. So I'm going to partition the job in this way. Or does this have to be done externally in the steering?
it should be done in external. MATGRAPH does not know that the CPU is supporting or AVX2 or AVX512 or how many GPUs, which GPUs isn't using. It should be calculated by someone who generate events.
Maybe I can take this as well.
Mm-hmm.
Yeah, Jin is right. I mean, at the moment we are compiling for a given vector size. Now, how are we gonna do this in collaboration? Because this would be really nice input from the experiments as well. How you would like to use MATGRAPH on the grid, so we could think about fat binaries or whatever is needed in order to make and then have a lay in front where you find your compute architecture and you load the right library. But this is really a discussion that we should have with you on how you would like to organize your productions in this case.
James, did you want to make a comment on
Yeah,
that?
I wanted to reply directly to this. So indeed, this the event generation step is pretty convenient for the big HPCs because there's no input data to ingress into them, and it's it doesn't involve huge I/O like reconstruction and simulation. So it's possible one could envisage that you would actually, you'd have a workflow where you really kind of know what kind of machine you're going to be running on in advance, and maybe wouldn't be sending out these jobs into the wild grid as we do with say reconstruction. That's just an idea. So maybe this is something that we could consider if we really want to try to make use of the big, in quotes, difficult HPCs for doing large scale event generation.
Yeah, very good point, James. Okay, time is getting on, but we could take one or two more questions if there are any. Just raise your hand. Of course, we don't have to. So if there are no more questions, then my thanks to Zenny and Jin again for the really nice talks, and to everybody for coming along and had the nice discussion that we had. So thank you. Let's close this HSF seminar, and then we will reconvene after the Christmas holidays and see you all again for more topics next year. Thanks, everyone. Bye-bye.
Thank you. Bye.
Thank you.